So Aritra and I have been working together on MongoDB since 2011, I think. We introduced MongoDB at FICO. We're still working with MongoDB, and today we want to talk to you about the Falcon Assurance Navigator product, which is one of our products and the one that we developed from scratch. And I heard earlier that you will retain about 20% of what we say here today. So we've decided to change the presentation to have the same 3 slides repeated 5 times so that you can really retain everything we say. You didn't know that, right?
I didn't know.
Last minute change. So FICO is known, I think, across the world for the FICO score, but that's not all we do. The FICO score is a small part of our business. We're very strong in fraud detection. We do credit card fraud detection, for instance. I've been doing that for 20 years. We've got 70% of the world market. We got 90% of the US market in credit card fraud detection. We have also lots of products for the banking industry, from loans originations to collections and recoveries. And we also move in the insurance world, healthcare insurance, etc. But the product we're talking to you about today is the Falcon Assurance Navigator, which is a fraud, waste, and abuse detection product for the procure-to-pay process and the expense reporting process. So because not everybody knows what procure-to-pay is, it's basically the whole cycle between the moment that you as an employee ask for something, submit a purchase request asking for computers or pencils or whatever, to the moment where that order is sent out to a supplier, the invoice gets back from the supplier, and the payment goes out to the supplier. So that's the procurement-to-pay cycle. And what we do is we analyze those transactions, and we try to detect whether there's been abuse or fraud or waste, anyone broke the rules, etc., and we give feedback in the form of a score or flagged rules. We also do the same for expense reports. So that's when you get home to your company and you submit your expense report. We do analyze expense reports and try to flag things that might be abusive or against the rules. We've started this product in a partnership with Stanford University, thinking that this was going to be for higher education only. But as it turns out, everybody does procurement, everybody does expense reports, and everybody has rules about it. So it's universally applicable as far as the business goal of the product is. We're still, for the time being, only working with universities. We've got a huge pipeline, but certainly we're going to expand this product to corporations because it can be very interesting. But what we mainly want to focus today is to talk about not only the product, but also what we do with MongoDB that gave us some advantage in the development of this product. So we're going to focus on the aggregation framework, we're going to focus on consistency, and we're going to focus on Atlas. Those are the main messages. Those are the 3 things that we want you to retain on this presentation. In order to prepare for that, I'll want to give you an overview of the architecture of the product. And this can be distracting. There's a lot of boxes, but I want you to focus on, so what's blue is MongoDB. That's where we do our persistence. And we've got our transactions, our queues, we've got cases, profiles, never mind what that means, but that's all in MongoDB. So in the beginning, there's a client environment where things happen, where the purchase requisitions are filled in, where the invoices come in, where everything happens in their systems, and that can be Oracle, Concur, SciQuest, you name it. There's a few in the market that operate in that area. Because our application accepts transactions in a standardized format, we need adapters from those systems in order to transform those transactions into the standardized format that FAN accepts. You see that's also blue, reference data, we have that in the adapter, so when a transaction comes with the vendor ID, we fetch the rest of the vendor information like addresses, bank accounts, contact people, etc., inject it in the transaction and send the whole transaction to, what am I doing here? Send the whole transaction to FAN. FAN works with transactions only, we don't do reference data. Inside FAN, we've got the engine, which consists of a series of microservices that communicate with each other through Mongo queues. So that's the first point where Mongo starts working. We get the transaction, we have a receiver that validates the transaction, puts the transaction in a Mongo queue. We've got what we call an attachment processor. The attachment processor picks up the transaction, sees if the transaction has attachments, the images that you scan and put in your expense report, for instance, and we grab the attachment, which can be in an external system, or it can have been uploaded to us previously. We grab that attachment, we OCR it, we store the transaction enriched with the attachment data in the transaction, and pass it on the queue, on the Mongo queue. And then we've got this third microservice, which is the context creator. What the context creator does is it picks up the transaction and it picks up all the transactions that are somewhat associated with this transaction, historical data or what have you, in order to create a context where our decision execution analytics engines can work on. Because sometimes we need to compare with what has happened before. We need to determine if there are duplicate invoices, things like that. So that whole context is then passed to a decision execution or an analytics engine to either run the rules that will determine whether you've broken any rules, or do analytics to determine whether this transaction falls off the norm and should be flagged because of that. Now, these are obviously all stateless microservices, and they run concurrently. Same with the decision execution analytic engine. We have more of them. We don't just have one set of rules, we have as many sets of rules as you want. And we have several analytics engines that can run all the transactions. Now, once the transaction has been thoroughly analyzed, it's decorated with a score that either tells us that it's an outlier or it's flagged some rules, and that is put in the database, back in the database. Then we have several sundry services that are not too important for this presentation. The only one that's probably important is this case manager. Case manager picks up the transaction, decides whether to create a case for that particular transaction, and that's also based in a set of rules. And if the case is created, it's then presented to case workers that go through the case and decide whether to disposition the case or call the police or the fireman or what have you, right? And at the same time, we notify the client environment of everything that happened, everything. So if the transaction is 100% kosher, it'll still be notified. So that and one of our clients has an event listener here and does actually give feedback to the users on how the transaction has done in terms of FAN. So this is in a nutshell the overall architecture. I'll pass now to Aritra because guy that actually had to implement this. I was just, from then on, my life was easy. I just came here.
Thank you. All right, so
Can we hear you?
can you guys hear me? All right. So, okay, so when we first created the application, it was created to be on-premise at Stanford. And we had a few challenges with that version of this application, 2.1. It was a monolithic application deployed on Tomcat. There were like 2 servers, one running the backend execution service, one running the case manager. It had a complicated stack, MongoDB, Elasticsearch, ActiveMQ, and we figured very quickly that the operational cost of asking our customers to run that stack was growing exponentially. We could not set up any kind of monitoring. It was like rudimentary, literally shell scripts, pulling information from multiple places and sending email notifications. So we said, okay, now we convinced our clients, all right, let's move to the cloud. After some convincing, they agreed to move to the cloud. And we set up a few design goals for us as we moved to the cloud, right? So the first goal was move to the cloud. Second was we wanted to have monitoring and reporting as the foundation. We wanted to have that end to end, right? We wanted to go to microservices. We wanted to actually use Kubernetes for this. So we made sure that this monolithic application would break up, be true microservices with all the scaling capabilities that comes with it, and then Kubernetes would do the orchestration. That's just to make sure that we can go on-premise again if someone asks for it, maybe. Also, it's a company direction. We wanted to reduce the operational cost, so we were looking for all available open source and paid third-party providers that could allow us to monitor everything. We wanted to have multi-tenancy. We wanted to optimize how much of our resources get used per service. So that's, again, some of the things that we get from Kubernetes. And then we started building compatibility with other expense and procurement systems. So we had compatibility with Oracle at Stanford, and then we started building these adapters that Carlos talked about. And we make progress there. And the last aspect was automation. This is when we said, okay, all right, we start with automation and then go forward. So the whole orchestration, write code, Jenkins, CI/CD with Spinnaker, deploy to Kubernetes, the monitoring infrastructure, everything was automated. So we started with these goals. And then we also had a bunch of monitoring and reporting requirements around it. So the first thing that presented us as a challenge, and the first thing where Mongo kind of shined for us, was our object model. So this is an expense report. Here, this is the expense report. An expense report can have multiple lines. Most of you would have filed an expense report sometime in your careers, hopefully, and you swipe your credit cards and it shows up as lines that you then say, okay, these are the dollars associated with this transaction, and I want to get it expensed, and the company pays you, right? Now, with universities, they have additional layers of, further down, they have these distributions, which is essentially saying, okay, I have spent $500 on this meal that I had. And by the way, I want to charge 50% of it on federal amounts, and 50% of it is a non-federal expense, right? So you're kind of distributing your expenses. So one of the first decisions that we made was to say, okay, this is a transaction. It comes to us. We are going to just take it and save it to Mongo. We are not going to try to normalize it, put it in separate tables, try to join them. Mongo gives us the capability of having this complex, deep nested structure, and it's actually like 4 levels deep, array inside an array kind of situation. And we said, okay, we are just going to take that and put it in Mongo, and then optimize it for queries and reporting and searches.
And if you see the gray boxes, for instance, they could be further expanded. We just didn't have enough space on the screen.
Yeah.
So we're talking about 6, 7 deep sometimes,
yeah,
when you expand those.
Makes sense. All right. So from a business perspective, we had all these requirements. We wanted to have We wanted to have insights around spend categories. We wanted to obviously detect outliers, detect potential waste and abuse. We had to provide some kinds of visualizations and dashboards to monitor how the case review process is going. We wanted to make sure that not everything's getting approved, hopefully. Our fraud detection analytics actually works, right? And also provide these aggregated metrics to the supervisors of the case managers, for example, of the case reviewers, right? And we had to do this kind of reporting all the way through, up to 4 levels deep sometimes. So this is a typical use case where we have to provide the workload on individual case workers. So the way the system works is transactions come in, right? They come into a queue. And this queue is assigned to a bunch of case workers. And then when the transaction comes in and it's detected as a fraud, we decide which queue to put it in depending on the expertise of the workers assigned to those queues, right? So here what you're seeing is kind of how many cases came into each of these queues, number of cases, dollars submitted, et cetera. So what you're looking at here is essentially this. We have a transaction, like a big JSON, which I have simplified here. And each case, right, created from that transaction has a status. And then each line in that transaction comes with decisions. It's approved or rejected, or whether it's in pending status. And then we try to aggregate by the case statuses, and then gather statistics on the decisions made on by these statuses and the amounts associated with them. So we started with this, and as you can see, the aggregation part and the reporting part gets pretty complicated. So for this use case, for this presentation, we are simplifying it to say, okay, let's just look at 1 level deep and what it looks like, right? So essentially, we start with a filter operation. We reduce the amount of data that we are aggregating through. Then we do a projection, further reduce the data that you are aggregating through, and then do a flattening with an unwind operation. So input and output. By the way, the Compass demonstration of the aggregation framework, debugging, that would be extremely helpful here. When we were constructing this, we were literally commenting out pipeline operators from a big pipeline and debugging each step. So with the Compass thing, it would be really nice. All right, so the next one was, again, we do another group operation, gather by statuses and decisions, add up the dollars here, and then add the unique case IDs to a set, because we want to get the unique case counts. We don't want to double count, so we were kind of aggregating by that. So that's another step in the pipeline. We move from this substate to this substate. And then finally, we do the final aggregation, another group by operation, gather by status, and then count the original IDs. So, that's it. This was the transformation with the aggregation framework. Back in 2011, when we started with the aggregation framework, it wasn't this powerful. We literally wrote MapReduce scripts, and this would be like 3 different MapReduce operations, one after the other, or maybe a map operation with multiple reduce operations. So as we progressed, we realized how easy it is for us to churn out reports like these, and we were able to generate reports like in 2-week sprints easily. So every 2 weeks, we could just create an aggregation pipeline, put it in, test it, and put it in production. Eventually, it required us to optimize things, but once we got it right, we were able to churn out reports just fast. Now, some of our power users, so some of our management level people also wanted reviews like these. So this is where you're seeing the case workers. Who is the caseworker, how many cases have they worked on, the amounts that they have approved, the amounts that they have rejected. So again, everything's just aggregation framework. This is another one. So this is actually, we are going about 3 levels deep into the object hierarchy, and we are aggregating by who prepared the expense report, how much of the money that they prepared for that expense report actually got rejected versus got approved, to just understand profiles of preparers. How diligent are they in submitting their expense reports? So this one, for example, is a pretty complicated pipeline. And obviously, we wanted to do this with efficiency, right? We also have power users who kind of wanted to have this, like they were coming from a world of SQL, so they wanted everything flattened. And we had to provide an interface, something like this. Obviously, behind the scenes, it's just translating it into a Mongo query, providing for efficient indexes backed by Mongo queries. But for them, it looks like a SQL-like query builder kind of thing, right? And then with some support for custom expressions. So yeah, I mean, that's the reporting part of it. I mean, with this, just by introducing the aggregation framework, we ended up with like a significantly reduced development time. As I said, like 2-week sprints, and we were churning out reports. We significantly improved the interactive performance. So we obviously had to do a lot of diagnostics. So Mongo explain plans and slow query monitoring over a period of time allowed us to figure out which part of the application is being used more and which queries are the most popular, and then we were kind of defining our indexing strategies based on that because memory is limited, right? We don't want to index everything. All right, so that was the reporting part of it. Now came the bigger challenge. So the reporting part was handled in the previous versions of the app. We just broke it down into microservices and we're done. Now, the bigger architecture part, which is like doing distributed computing and doing it without introducing any kinds of faults in the system. Remember, dollars are flowing into this, so it's not okay. Unlike clickstream data, for example, you miss the results from 2 or 3 clicks, no one really cares. But sometimes, it depends on the use case. In our case, we cared about transactions. We couldn't lose anything, right? So we wanted to have fault tolerance across the board. So for the first thing, also we realized that the first step that we could do was to simplify our stack. So we had Elasticsearch, we had ActiveMQ. We realized quickly from our experience on premise that we weren't really using the power of ActiveMQ. The volumes, like the number of expense reports in a university as big as Stanford, like it's still small. I mean, you don't file 1 million expense reports a day, right? So we could deal with the volumes with Mongo queues, and that was one of the decisions that we made. We said, okay, let's simplify, not use ActiveMQ, you just use Mongo queues and see where it takes us. And it performed enough that we just could switch to it, right? It simplified our stack, it simplified monitoring, because instead of monitoring JMS queues, we are basically monitoring our Mongo infrastructure, which is just there, right? It introduced a few issues. One was consistency. How do we make sure that when we are persisting our transaction and when we are persisting it into a queue, it's like a 2-collection persistence. How do we make sure that they are consistent, right? How do we make sure that we don't lose data or we don't choke up the system because one of the operations is failing continuously? The other issue was polling. So this is before change streams. We built this with Mongo 3.2. I'm sure if we move to change streams, move to Mongo 3.6, which is in the pipeline, we will probably be able to fix this in a better way. Okay, so we introduced, the first step was towards fault tolerance was to introduce a journal. So these are all the services that we go through, right? We ingest the data, we run OCR on it, we run our NLP services on it. This is our text analytics engine. And then we run decisioning on it, which is like our rules engine. We do analytic operations. This is outlier detection. And then we have the events, which goes back to the customers. And then, of course, we have our case manager. So what we wanted to do was to make sure that we can tag the transaction as it flows through the whole data execution pipeline. And it would give us 2 benefits. First, it allows us to recover transactions, which I'll talk about in a bit. And the second is it allows us to also retroactively monitor quality of service, because we can now know how much time is a transaction spending in each of these services, and then we can accordingly target and optimize those services to perform better maybe, right? In some cases like OCR takes time. If you have a 50-page document, it might take up to 15 seconds to get back the results. With small documents, it's like 500 milliseconds. So we always had to get these kinds of metrics. So we introduced the journal, and that gave us the capability to have quality of service reporting and to also set us up for recovery scenarios. All right, So addressing consistency, there were two scenarios really. One was a transaction comes in and the same transaction gets resubmitted by the customer, right? And we wanted to make sure that they don't step on each other's toes and we don't do stale writes. So that's really a locking scenario on a single document. So we addressed that with optimistic locking. And the other was like two-phase commit like scenarios, and we wanted to figure out, can we simplify that? So Morphia was easy. We take a document, annotate it with a version tag, and whatever. And then when we try to persist the document, if we get a concurrent modification exception, we say do something with a policy, and the policy is kind of externalized by a framework called failsafe that we are using. It's like an open source framework. So with externalized policies and some retry policies that supported by Morphia, we could just address optimistic locking. This was easy. The problem was the two-phase commit scenarios. The receiver's writing to a transaction collection, and it is writing to a queue. The attachment processor is picking up from the queue and doing something, and so on, right? So there were some simple scenarios which we found were like not really two-phase commits, right? So this is a scenario where I have this context creator persisting to a transaction collection and then persisting to a queue. Well, what could go wrong, right? Well, this could fail, or this could fail. If this branch fails, doesn't matter. It's recorded in the journal. The journal knows it has not been processed by it hasn't been processed by the transaction creator. So we just monitor the journal. Things break, we just resubmit. As long as our service is idempotent, and that is key, as long as our services are idempotent, resubmission is never an issue. So we just built idempotency, spent some time doing that. And then it was easy. Did not go to the queue, fine, it's not recorded in the journal, so just resubmit. Now this was a slightly more problematic issue. We have this event listener which picks up from the queue, makes a decision, is it a case, is it not a case? If it is a case, delete. If it is not a case, then persist the case and then delete. Now, there are 3 persistence points here that could break, right? And we had to explicitly mark the transaction as busy in the queue and then go back to the case, say yes or no and delete, right? And then we had to set up a cron job that would say, do I have a transaction in the queue that is in busy status and it also exists in the case collection? Yes, which means I have processed it correctly, but I haven't been able to delete it here because maybe this delete operation failed. So okay, I can just delete it because I see it in both collections. Another scenario, is it in busy and has been busy for a while? Okay, resubmit, right? Because it's not in the case collection, so nothing's wrong, I just resubmit. It's idempotent, so nothing's lost. On the resubmission, hopefully the case again makes a decision that it's a no, so the delete goes through. So we had to work out all these scenarios to figure out, what simplifies it, what are the situations where we don't need to rely on the journal to recover things, and so on. Now, so basically, with these two-phase commit scenarios, right, there was no one-size-fits-all solution. We were essentially going through like use cases, creating decision boxes, drawing flowcharts, brainstorming, spending days sometimes to, or maybe. So the other issue was eventual consistency. We had to live with the fact that eventual consistency is good enough. Yes, the system can become inconsistent, and there are situations where our transaction could get stuck. There is a situation where I just get stuck in a queue and something's broken, so my monitoring says, hey, there is a high latency there because this service is not picking up in time, right? So things were getting stuck, and it was kind of hard. The recovery process is getting kicked again and again. And that's like intensive, resource intensive. Idempotency is key. If this was like an at least once kind of an architecture, we would be burnt. I mean, at least once is super expensive, and then trying to build our own logic on top of at least once would be really hard. And basically, we were working through these complex recovery scenarios. So when Mongo announced about ACID, we were on cloud 9, right? And essentially, from all this spaghetti, well, the code was okay, but the logic was crazy. From all of that, we got into the beta program, and we tried this out, and our code became elegant 4 lines. Start a session, commit a session, and in between, just process to those 2 collections. And we were like, yay, significant simplification achieved. All right. So one of the other things I mentioned, Elasticsearch, that's been, another thing that we need to manage, and we are not that big a development team, so we said, okay, can we simplify it? And we started looking at the documents, right, that we get out of the OCR process. And we were scanning, the biggest documents we found were like 2 megabytes. So initially, we had anticipated that there is a situation where we could exceed the 16 megabyte limit of a Mongo document, right? And that's why we were putting the text content into ES. But then we figured out after the system ran in production for a year or so that, well, the documents, the OCR text is not that big, so we could just, put it in the same document as a transaction and just use Mongo's searches, Mongo's text indexes. So that's work in progress. It's scheduled for our next release. And this essentially says, we just simplify. We got rid of ActiveMQ. We did not need it. We can get rid of Elasticsearch because we weren't using it the way we wanted to use it earlier, that we thought we would use it. And we just go to the text indexes. All right, so the last bit was Atlas. So when we moved to the cloud, we did a bunch of POCs to understand whether it fits the bill from various angles, right? One was performance, one was how do our operations teams work, and the third most important thing was security. So with our initial review, obviously from an operational perspective, it was a no-brainer. We just said, yeah, this is great. Performance, we initially had issues. We said, what's going on? Why is it slow? And then we talked to our Mongo consultants, and they said, hey, are you doing VPC peering? We just introduced that, and we said, oh, okay, that seems like we are in the same VPC. It's nice. So the performance issues were gone. We ran a bunch of, just bombarded the system with like 100 times the load that we have ever seen, and it just worked. Backups was excellent, right? This is kind of the selling point. We did not have to figure out our own backup policies. We actually had a situation where some staging environment pointed to another staging environment, which it was not supposed to point to, and then introduced weird artifacts, and we actually rolled back to the primary staging environment based on the backups. And then tenant provisioning, we can now automate it with scripts, basically, right? So yeah, with the move to Atlas, I think the last bit is security, and well, we had some announcements there this morning, and I think some of the security issues would be resolved by that. So yeah, I mean, overall, I think for us, move to Atlas kind of made a lot of sense, and we said, okay, yeah, we'll do it. And so far, things have been stable, right? We are looking for Mongo 4.0, and once it gets released, we can introduce the transactions and all that and simplify our code. That's it. Do we have time for questions? All right.
Thank you, Aritra. Does anyone have questions for either Carlos or Aritra?
Great.
No questions? One question.
There is AWS Lambda functions, which seems to be like a next logical thing in your architecture. What do you think about this?
So the thing with Lambda is it is very AWS, right? So our strategy is to use Kubernetes and have everything in Kubernetes as much as possible. Having said that, we are using Lambda for some
once the architect went rogue, not the developers. We are using Lambda in our transformation layer. So the transformation we have a kinesis flow that basically takes the transaction into a lambda that does the transformation and spits out the JSON that kinesis flow pumps back into fan. If you remember that middle layer, that's where we're using lambda.
Yeah.
And that's a lot of lambdas because we have numerous transformations. I mean,
Yeah.
10 or 12 transformations. So it's a lot of different lambda functions. But yeah.
Any other?
Hi, would you mind telling us about the size of your Mongo topology, like number of nodes, size of databases, etc.?
We are using
M4, M5, something like that.
M50 or something like that, I think. I have to check that. We are sizing it in Atlas, and
Yeah.
we have resized it a few times now. We are still trying to figure out what's the right size for us in Atlas. On premise, it was being managed by the customers, but in Atlas, we are still, we have resized it a couple of times, and it seems to be okay. So yeah. No, we figured that we don't really need sharding yet, right?
Not for FAN.
Not
We
for
have to understand FAN is an application, because we're doing procurement to pay for universities at this moment. We don't have massive amounts of transactions. Where we do have massive amount of transactions, another application that we're also working on that does case management for compliance systems, and that's the transactions that are in the millions or billions even, and that's where we start looking at sharding, and we've got a separate deployment architecture team that does all those calculations and things. Yeah.
Any other questions?
In an absence of change stream, how did you implement the polling?
Sorry?
In an absence of change stream, you said you had polling mechanism.
Polling methods? Oh, okay. So you can do it in two different ways. One is just polling with code, right? The other one is to use like capped collections, because capped collections will give you a cursor, and then you can just monitor the cursor and use that as your queues. So actually, there are some nice Mongo documentation that talks about using Mongo collections as queues, and we just piggybacked on that.
And remember, change streams is nice, and it's a nice API, but the oplog has been there forever.
Yeah.
And we have abused the oplog, I have to admit. We've had listeners on the oplog that are doing what change streams made easier.
Yeah.
Thank you very much, Carlos Saraiva.
Thank you.
Aritra Chatterjee.
Thanks.